Let's start the exercise questions. First question is, Bohr radius is given by this formula. Verify that RHS has the dimensions of length. So this is the first one. We need to verify using the dimensional analysis. So A naught is epsilon naught h square over pi m e square. Now let's write the dimensions of all these quantities. M L square t minus 1 whole square upon pi is dimensionless. Then we will have M L square M L t minus 2 into M A t whole square. So once you simplify this, you will obtain m square L की power 4 to t to the power minus 2 m square L cube t minus 2. So L will come. So ultimately we get the dimension which is equal to that of a length. So therefore A naught has the dimension of length. In question 2, we need to find the wavelength of radiations emitted by hydrogen in transition from n equal to 3 to n equal to 2, then n equal to 5 to 4, then 10 to 9. So the second question, we know that wave number is given by 1 over lambda. So 1.1 into 10 to the power 7, and this formula can be used here, n1 square minus 1 over m2 square. So this formula can be used. So first A part, n1 is 2 and n2 is 3. So 1 over lambda equal to 1.1 into 10 to the power 7, then 1 over 2 square is 4 minus 3 square is 9. So lambda will be 36 over 5 into 10 to the power 7, 6.54 into 10 to the power minus 7 meters. So lambda is equal to 654 nanometers. B part, n1 is 4 and n2 is 5. So again 1 over lambda 1.1 into 10 to the power 7, square of 4 is 16, square of 5 is 25. So once we solve this, lambda will be 400 over 1.1 into 10 to the power 7 into 9. So it will be 40.404 into 10 to the power minus 7 meters. So lambda will be around 4040.4 nanometers. In the third part, n1 is 9 and n2 is 10. So 1 over lambda equal to 1.1 into 10 to the power 7. Square of 9 is 81, square of 10 is 100. So lambda will be 8100 over 19, 1.1 into 10 to the power 7 into 19. So it will be around 387.559 into 10 to the power minus 7 meters, or lambda will be approximately 38755.9 nanometers. Remember, we have taken here, this is R, okay. So we have taken R to be equal to 1.097 or 1.1 into 10 to the power 7. In question 3, we need to calculate the smallest wavelength of radiation that may be emitted by hydrogen, then helium ion, and then lithium ion. So this is the third one. So if you want small wavelength, then it means largest energy, most energy, highest energy, whatever you call it, highest energy, because energy and wavelength are inverse of each other. So this means n1 will be 1 and n2 will be infinity. So A part 1 over lambda r 1 over n1 square minus 1 over n2 square. So 1.1 into 10 to the power 7, 1 over 1 square minus 1 over infinity square. So from here lambda will be 1 over 1.1 into 10 to the power 7. So it will be around 0.909 into 10 to the power minus 7. So wavelength will be around 91 nanometers. Then B part 1 over lambda. For other atoms we have this formula, okay. For other atoms this formula is there. Z also comes. Because for hydrogen Z is 1, so 1 square is 1. So lambda will be, after putting all the values, 1 over 1.1 into 10 to the power minus 7 Z square. So it will be 91 nanometer, and helium's atomic number is 2. So 2 square will be 4. So wavelength will be 23 nanometer in the case of helium atom. And for lithium it will be 91 nanometer over Z square, and its atomic number is 3. So 91 nanometer over 9, 3 square is 9. So lambda will be approximately 10 nanometers for lithium ion. In question 4, we need to evaluate the Rydberg constant by putting the values of fundamental constants in its expression. Fourth one. So Rydberg constant can be obtained by this equation, where all of these quantities are some constants. So mass of electron is 9.1 into 10 to the power minus 31 kg. Charge of electron is 1.6 into 10 to the power minus 19 coulomb. So to the power 4 over 8 into h is 6.63 into 10 to the power minus 34 whole cube. Speed of light is 3 into 10 to the power 8 meter per second, and epsilon naught is 8.85 into 10 to the power minus 12 square. So what we will obtain here is R will be approximately 1.097 into 10 to the power 7 per meter. This will be the value that we obtain from putting all the values. In question 5, we need to find the binding energy of hydrogen atom in the state n equal to 2. So this is the fifth one. N1 is 2 and N2 will be infinity, because in binding energy when we calculate we will take out the electron, so it will tell us how much energy is required to completely take out the electron. So this is the formula for finding the energy, 1 over N1 square minus 1 over N2 square. So what we will have, energy will be 13.6, 1 over infinity minus, this should be 2 and this should be 1 over 4. So energy will be minus 13.6 over 4. so minus 3.4 eV. In question 6, we need to find radius and energy of helium ion in the states n equal to 1, 4 and 10. So this is the sixth one. A part, n is equal to 1. We know radius is epsilon naught h square n square over pi m z e square, or it can also be written like 0.5 n square over z in angstrom. So when n is equal to 1, r will be 0.53 into 1 square over, for helium atomic number is 2, so r will come out to be approximately 0.265 angstrom. Remember, this is in angstrom. Angstrom is 10 to the power minus 10. Next, after this, epsilon energy minus 13.6 z square over n square. So minus 13.6, atomic number is 2, so 2 square 4 over n is 1, so it will be minus 54.4 EVs. Next, B part, here n will be 4, so radius will be 0.53 into 4 square is 16 over 2, atomic number 2, so it will be 4.24 angstrom, and energy will be minus 13.6 into 4 over 16, so it will be minus 3.4 EV. C part, n will be 10, so r will be 0.53 into 10 square is 100 over 2, so it will be 26.5 angstrom, and energy will be minus 13.6 into 4 over 100, so minus 0.544 will be the energy. This is in EV. So these are the values that we get. In question 7, hydrogen atom emits ultraviolet radiation. What are the quantum numbers of the states involved in the transition? So this is the 7th question. Now we know this formula for hydrogen atom. Now wavelength is given 102.5 into 10 to the power minus 9 equal to r is 1.1 into 10 to the power 7 1 over 1 square minus 1 over n2 square. So from here we will have like this 1 minus n2 square. So 1 minus 1 over n2 square will be 100 over 102.5 into 1.1. So 1 over n2 square will be 1 minus 100 over 102.5 into 1.1. So n2 will be 2.97, or you can say 3. In question 8, we need to find the first excitation potential of helium ion and ionization potential of lithium ion. So this is the 8th one. A part, first excitation potential of helium ion. So it will be equal to 10.2 into z square. So 10.2 into 4 because its atomic number is 2. So 2 square is 4. So it will be 40.8 volt. And for ionization potential of lithium ion, we will have 13.6 into V EV into Z square. So it will be 13.6 into 3 square, that is 9. So it will be 122.4 volt. In question 9, a group of hydrogen atoms are prepared in n equal to 4 states. List the wavelengths that are emitted as the atoms makes transitions in return to n equal to 2 states. So this is the ninth one. N1 equal to 4, N2 equal to 2, N1 equal to 4, and let's first solve this part only. So 1 over lambda equal to 1.097 or 1.1 into 10 to the power 7, 1 over 16 because 4 square is 16, and 1 over 4 because 2 square is 4. So 1 over lambda 1.097 into 10 to the power 7 into 3 over 16. So lambda will be 16 into 10 to the power minus 7 over 3 into 1.097. So the wavelength will come out to be approximately 4.8617 into 10 to the power minus 7 meters, or this can be 487 nanometers. Now what if N1 is 4 and N2 is 3 now? This was one situation, this is another situation. So same 1 over lambda 1.097 into 10 to the power 7, 1 over 16, 1 over 9 because 3 square is 9. So 1 over lambda will be 1.097 into 10 to the power 7 into 7 over 144. So lambda will be, after solving, 1875 nanometers. Now if N1 is 3 and N2 is 2, what then? So in this situation 1 over lambda 1.097 into 10 to the power 7, 1 over 9 because 3 square is 9, 2 square is 4, so minus 1 over 4. So 1 over lambda equal to 1.097 into 10 to the power 7 and into 5 over 66. So wavelength will come out to be, after solving, 656 nanometers. This wavelength will come after we solve the equation. In question 10, we have a positive ion having just one electron. It ejects it if a photon of wavelength 228 angstrom or less is absorbed by it. So we need to identify this ion. So this is the 10th one. First of all, wavelength is 228 angstrom. We know that energy is Hc over lambda. So 6.63 into 10 to the power minus 34. By the way, 228 angstrom means 228 10 to the power minus 10 meter into 3 into 10 to the power 8, which is the speed of light, into wavelength 228 into 10 to the power minus 10 meters. So energy will come out to be 0.0872 into 10 to the power minus 16. Now transition takes place from n equal to 1 to n equal to 2. So what we will have, 13.6, 3 by 4 Z square equal to 0.0872 into 10 to the power minus 16. So Z square will be 0.0872 into 10 to the power minus 16 into 4 over 13.6 into 3 into 1.6 into 10 to the power minus 19. So Z square will be 5.3. So Z will be root 5.3. So Z will be approximately 2.3, or you can say Z equals 2. Z equals 2. So if Z is 2, this means it is helium ion.